So, so there's a question that says two capacitors A and B are connected into the circuit as shown. The capacitor A has a capacitance C and B has a capacitance 3C. Okay, the electromotive force is V. Okay, the two-way switch S is initially position X and the capacitor B is initially uncharged. State in term of V and C the expression for QA. Okay. I think that's gonna be easy. So we can say that capacitance, okay, there's 3C, okay, and that is C. That is C and that is 3C, right? So QA is equals to C and then V. Okay, simple thing. Initial energy stored. So E is equals to half CV squared, or QAV can also be. Okay, the two-way switch is now moved to the position Y, is now moved to the position Y. State and explain what happened to the charge that was initially on the plate of the capacitor A. Okay, so so as this capacitor A become fully charged with a voltage V across it, okay, and when you connect this switch right here, okay, then due to this voltage, it will start discharging and the charge will flow through the second capacitor, okay, and it will store in the second capacitor basically, right? So until the new voltage should be the same for both of them, right? Because the potential difference or the charging process continue till the 2 points have the same potential difference, right? So in this case, this capacitor should have the potential difference that is of the same value as this one, right? But initially we have the greater voltage, so this has to decrease from V to some new voltage, and this has to increase from 0 to that new voltage, right? So, and this has to lose the charge, and this has to gain the charge, right? From 0 to some value, and this has to lose the charge from Q A less than some value, right? So let's try to solve. Okay, so explain what happened to the charge that was initially okay. So the charge will start flowing from A to B, okay, until the potential difference of A and the potential difference of B remains the same, become equal, right? So we can say that the charges start moving from plate A, sorry, capacitor A to B, capacitor A to B, right? First thing, and this process continues until the PD across, come on, across A uh, and PD across B become equal. Okay, so now they're saying show that the final potential difference across the capacitor B is given by this expression. Okay, and explain your working. So we have to explain that we know that the two capacitor will have the same potential difference, by the way. Okay, so the two capacitor VA should like this. Okay, so VA should be equal to VB, right? So the total charge that is basically in the form of QA, right? Because initially capacitor A charges, right, due to that battery, right? So that charge QA is basically considered as the total charge of the two capacitors, okay? And that is equal to CV, right, by the way. So this total charge will then be distributed into two things, okay? The um, charge on A plus charge on B, right, should be equal to, should be equal to the total charge that is going to be QA, right? So wait, let me just rewrite this. The charge on A plus charge on B is equals to the total charge, which is CV, right? Okay, this is the total charge, right? Now, over here, the charge on A is going to be CV plus this is going to be um, 3CV, right? Because they mentioned that the capacitance is 3, right? The voltage remains the same, right? As we are considering both will going to have the same voltage, right? But okay, we have to take the voltage VA and VB as well. Okay, so I'm taking this as VB, and okay, there should be VB as well, because um we know that the potential difference has to be equal, right? Till the charging process, okay, and when they become equal, the charging will be zero, right? So is equals to CV, okay. So C and C goes off. So you'll be left with VB is equals to V over 4, right? Okay. So this is the first thing. Now the last part is determine an expression in terms of C and V decrease for the decrease in delta E in the total energy that is stored in the capacitor as a result of the change of the position of the switch. Fine. Acha. So the decrease. So initially we have the energy half CV squared, right? This is the initial energy, right? And initial, okay, this is the initial energy, right? Now the energy after some instant is going to be, mm, 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 mm. Okay. Finally, we know that the two capacitors are basically in parallel, okay? So their capacitance will be added, okay? And okay, if we consider the capacitance being added, so, and we know that their potential difference is V over 4. Okay. So, wait, can't it again? Okay. So finally, I have 1 over 2 into 4C into V over 8 squared for the capacitor. Okay, for the V over 4, not 8. So if I solve, I will get 4C into V over 16. 4 1 are 4, 4 4 is a 16. Okay, and then it's going to be 1 over 8 CV, right? So this is the final, that is the initial. Okay, if I try to find out the change in energy, so change in energy is going to be 1 over 2 CV squared minus 1 over 2, 1 over 8 CV squared, right? Okay, so that should be 4 3 over 8 CV squared, right? So that is going to be 3 over 8 CV squared, right? So, yep, this is the concept. Now, moving on to this question. The capacitor C is charged so that the potential difference across the terminal is 8. Okay. Okay, fine. The switch is open, initially open. The switch is closed at time t equals to 0. Okay. Show the variation. Okay, fine. So we have, okay, we know that the gradient of this graph is going to be 1 over the capacitance. Okay. And, mm, okay. And show that the energy stored in the capacitor at time t is equals to 0 is 1.8 volt. In the capacitor C. Okay. So at time t equals to 0, there's a voltage of 8 volt. Okay. And we have to work out for the capacitance. Okay. So we can use the gradient for the capacitance. Okay. So gradient is equals to, okay, 200 and 1, 2, 3, 4, 5, 2, 1, actually 2.4, 2.8, 3.2, 3.6, 3.6. Okay. So, so 200 coulomb, 200 microcoulomb of charge. Okay, minus divided by 3.6. I'm directly doing the reciprocal thing, okay, to get the capacitance directly, okay. So 200 exponent negative 6 divided by 3.6. So I am getting 5 exponent 5, or we can, this is the capacitance, by the way. The VD across terminal of the capacitor is 8, okay. Oh, if we can also use this value, which is 1 point 400 and 420, 440, 450. Okay, so 450 is the charge value, so we can directly use the charge value. Okay. So 1 over 2 into 450, right, microcoulomb, and into 8, right? So at time t equals to 0, there's a 8 volt there's a 8 volt across it, right? So you can solve. So I'm getting 1.778, which is rounded off to 1.878 exponent negative 3. Okay, that is going to be 1.8 exponent negative 3, and it is proved, right? Now, they're saying determine the capacitance of the capacitor C, give your unit, and give a unit with your answer. Okay. So for that you can use a gradient. Okay. So we basically have to use a gradient in this part. Okay. So gradient is equals to 1 over c. We know that. Okay. C is equals to 1 over the gradient. Okay. So 1 over the gradient mean x-axis on the top and y-axis on the bottom. Okay. So 200 exponent negative 6 divided by 3.6. Okay. So that is going to give me 5.6 exponent 6 negative में, and there's going to be farad. Okay. Now they mentioned the graph of ln function. Okay. And show that when t is equal to one time constant, the value of is 1. अच्छा जी, okay. So we know that v is equals to v naught e power minus t upon rc or tau. Okay. Do we have the values of the capacitor? We have the value of the capacitor. We don't have the value of the resistor. Okay, so fine. So we can use RC thing. Okay, but we know that the initial voltage is V naught. Okay, so that is going to be 8 E minus T over tau. Right now they're saying show that when T equals to one time constant. Right. So this whole thing become one. Okay, because when both of the thing become one time constant, so this whole thing will be negative one, right? And that's okay. Wait. V naught, and that's it, right? Now if we try to solve, so V over V naught is equals to e power minus 1. Okay, so what can I do? Okay, that is going to be 6.63. Okay, if I put L in both sides, so I'll get ln V over V naught is equals to negative 1, right? And from this point, ln V, then minus ln 8, and then minus ln V. Okay. No. Okay, so the variation of this, okay, if we try to relate that, V is equals to 8 e power minus t upon tau. So, um, V over 8 and that is ln is equals to minus t over tau. Okay. So, this that they have the negative line. Okay. So, when t is equals to one time constant, when t is equals to one time constant, okay, the value of ln, okay, so we basically have to figure out at which time when t is equals to one time constant, okay. So I'm getting negative one, so this negative one will be right here, okay. Show that when t is equals to one time constant, so I put t is equals to one time constant, and I ended up getting this value where um where I have ln v over v naught is equals to negative 1. So this negative 1 is Actually, it should not be the negative one. Um, but due to the fact that it also have the negative sign, so the negative and negative will ultimately cancel out, or we don't have to worry about the negative sign then, right? Because it is a negative axis by the way, right? So so this is just one. We consider t is tau, right? So both the things get cancelled out, and there's one left. Okay, so that is why this one negative one basically shows that this is the time constant, right? So this is the time constant, right? Now, or okay, so if I read this from the graph, so 2.246833.2. Okay, so it is going to be 3.2, right? So now they're saying determine the time constant. So 3.2 directly from the graph. Resistance of the resistors are okay. So we know the capacitance 5.6 exponent negative 6. We have this value. So this is equals to 3 RC. Okay. And 3.2, come on, divided by R, which is going to be found, and C is 5.6 exponent negative 6, right? So if I calculate it, so I am getting this value as 5.7 exponent 4. I'm getting this as 5. Wait. 200 exponent negative 6. Okay, 5. This is 5, not 6. Okay, this is also 5 and not 6. Then it should be 5. Okay, fine. Now, that is done. Okay, last question. Okay, let's try. So now they're saying, show that the capacitor of the capacitance C connected in series with the resistor of the resistance R. Okay. Initially, the switch is open, and when the potential difference of 12 volt across the capacitor, the switch closes. Okay, fine. They have given us the current. Find the shape of, explain the shape of the graph. Okay. Okay. So to explain the shape of the graph, um, okay, we have to relate the things. So as we switch on, so the capacitor will discharge. Okay, and the potential difference across the capacitor will be directly proportional to the charges. Okay, and okay, and so yeah, we can say that the PD across the capacitor will be same as PD across the Acha, across the capacitor will be same as PD across the resistor. Okay, now so we also know that the current and PD across the resistors are proportional, right? So the rate of change of current at the capacitor will be same as rate across the resistor. Okay, so that's it. Now, okay, so determine the R. Okay, we have 12 volts, and we can find the initial current. Okay, so that is going to be 1.13 milliampere. Okay, 0.13 exponent negative 3 is equals to R, so that is going to be 12 divided by 0.13 exponent negative 3. So I am getting 9.2 exponent 4. Okay. Now they're saying the time constant. Okay. So to find the time constant, we have to do a lot of things. Read off from the graph. Okay, let's see. Initial current. Okay. V is equals to V naught. Sorry. I is equals to I naught e power minus t upon tau. Okay. So I have the initial current as 0.13, 0.13. I am considering that t is equals to tau. Okay, so that become negative 1. In order to find out I'm doing that way. Okay, so now 0.13. Bro, it's actually the current graph, so we won't. It's actually the current graph, so that's why. So basically, area of this graph will give you the charge, but it would be difficult. Okay, so don't go for that. Okay, so 0.13 exponent negative 3, negative 1 is basically, sorry, 0.13 and then exponent negative 1. So I'm getting I as 0.0478. Okay. So, and milliampere. Okay. So now at this current, we will have the time equivalent to time constant. Okay. So point one, point zero, 1, 0.02, 0.03, 0.04, approximately at this point. Okay. So this is going to be one time constant. Okay. 2, 4, 4.2, 4, 6, 8, 4.6, 4.8, sorry, 4.8, right? So this is the value of 4.8. Point one and one, two, three, four, approximately point 0.5, which is going to be okay, approximately 0.47, 0.48. Okay, so approximately 0.47, right? seconds. Okay. Now we know that T is equals to RC. So 0.47 divided by resistance is going to be 9.2 exponent 6 exponent 4. 9.2 exponent 4 is equals to C. Okay. So the C then will going to be 0.47 divided by 4. Okay. So I am getting the capacitance value as 5.1 exponent negative 6. Okay. And that's it. These are all the questions of the capacitance, discharging of the capacitor, right? I have sent the worksheet as well. Okay. Or if you have your questions, then try as many questions as possible at your home. Okay. For the capacitance. Okay. And discharging of the capacitance mainly. And yep, that's it. So that's it for today's class. Okay, we're going to start the next chapter in tomorrow's in the next week class, and I set it the test on Friday, right? Please keep in mind. Chal, that's it.